This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, and this is Lecture 30, where we're going to talk about extreme ultraviolet lithography, usually referred to as EUV lithography. As we've seen in the last couple of lectures, we are hitting a resolution limit with our current technologies. We currently use a wavelength of 193 nanometers from an argon fluoride laser, and we've been able to raise the numerical aperture using immersion lithography up to 1.35. As we also know, K1 for the half pitch is limited to 0.25, which means the resolution using the Rayleigh equation is something on the order of 36 nanometers, a little bit bigger than that. Well, that's kind of where we're stuck right now. We can do maybe 38 nanometer half pitch as the smallest feature sizes that we can print in terms of half of the pitch. But it can't go below 0.25 for K1 unless you use double patterning. And as we saw, double patterning, while it works, is very expensive, so we'd like a cheaper solution than that. Numerical aperture can't go above 1.35 unless we developed higher index lenses and fluids, and we don't have that available to us today. So the next question is, can we lower the wavelength? Is lowering the wavelength a possibility in terms of improving this resolution? Well, for a while, the industry worked on using a fluoride F2 laser. 157 nanometers is the wavelength. You can see that's an improvement over 193, but that turned out to be too little bang for the buck. 157 is only a small improvement over 193. It has a lot of problems in terms of lens materials, in terms of absorption by oxygen in the atmosphere, and finding a good pellicle that will work on the photomask. And we don't have as good an immersion fluid. So 157 can't use water as the immersion fluid, for example. So 157, while we spent several years trying to develop it as a lithography wavelength, that effort has been abandoned, and we're no longer looking at it. Well, what could we do next? As we go further lower in wavelengths, we run into a lot of problems. We find that we can't use glasses, normal kinds of glass, like fused silica, even fluoride glasses, calcium fluoride, anymore. And instead, we have to use only mirrors because we can't find a good optical material that refracts. We can find materials that do reflect. Excuse me. Those mirrors become difficult to manufacture as the wavelength gets lower, and air starts to absorb at these low wavelengths. So we have to start operating our systems in vacuum, which is also difficult and complicated. So if we're going to do this, we might as well push the wavelength down really low. And that's where extreme ultraviolet comes in. The idea is to use a very low wavelength, in this case 13.5 nanometers, and that requires all new optics, a whole new way of making and thinking about the mask, the biggest problem, the source of light, and of course different photoresists as well. All of these things change every time you change the wavelength, and this change of wavelength is extremely complicated. Here I show a scanner being developed by ASML Lithography with a light source here shining up into the optical system. You see it's all mirrors reflecting around. The reticle is up here and the wafer is down here. It's a massive system, about twice as big as a 193 immersion scanner, and quite expensive as well. These tools are under development. They're not quite ready for prime time yet. And we're going to talk about some of the challenges associated with bringing these tools into production. So, first, the optics. As I said, we can't build lenses that use 13.5 nanometer light. Instead, it's all reflective. Here's the light source here. I'll talk about the light source a little bit later, but it emits light going in one direction. The intermediate focus is where we often measure how powerful our source is. We talk about how many watts are at the intermediate focus. Then we go through a set of reflections for our illuminator. A reflective mask so it bounces light instead of transmits light. And then a projection optical system with a wafer stage down here. It's a step and scan tool, just like we use in immersion lithography. And the first prototypes, the first beta tools that are in the field now have a numerical aperture of 0.25. The production tools, which are being shipped as I speak, the end of 2013, the beginning of 2014, have a numerical aperture of 0.33. Well, you work the numbers on the Rayleigh equation and you find that the resolution is a little bit better than a factor of 2 beyond what you can do with 193, today's immersion lithography. So this means that we could use EUV lithography instead of double patterning. Now, the problem is EUV lithography is not ready. We need double patterning now, so we're using double patterning in production as we speak. The resolution is a little bit better than a factor of 2, improved compared to 193. So in fact, we could use EUV lithography for the next generation after double patterning if it's ready in time. In that sense, it might be an option instead of quadruple patterning, which is one thing people are talking about, or maybe some other option that this will be better than. So if we can solve all the problems, get it ready for manufacturing, it could be that EUV lithography will be the generation after 193 double patterning. But it's a big if, because there are some very significant problems remaining, and I'll try to describe those in the next few slides. First of all, as I mentioned, EUV lithography involves all reflective optics. It also involves a reflective mask. How do we make a mirror? Well, we can't just find some material like aluminum or copper or something that reflects. In fact, it takes a lot of work to do a good job of reflecting UV light. We use what's called a Bragg reflector. That is, we have alternating layers of molybdenum and silicon. Each of these layers are on the order of 2 nanometers thick, and then we have 50 or 60 or 70 of these layers to build up our mirror. The result is a reflectivity of about 70%, a little bit less than 70% at its very best. So if we do everything right, we can get close to 70% reflectance. It's a very strong function of wavelength, and so you see we've purposely picked the wavelength that has the maximum reflectivity for this molybdenum silicon multi-layer mirror system. Now, if your reflectivity of one reflection is 70%, that means your intensity of light gets cut in half every 2 bounces. Here we show an imaging optics of 6 mirrors, so that is 2 to the 3rd reduction, about 1/8 of the light going through the optical system. But of course, the mask is a mirror as well. It has a maximum of 70% reflectance. So all 7 of those reflections give an 8% transmission. But there's also 4 mirrors in the source system, which has a total transmission then of 25%. So the total transmission from intermediate focus to the wafer is less than 2%, approaching 1%. As you might imagine, that means we're going to need a pretty bright source just to survive all these reflections and still have a lot of light hitting the wafer. And as we'll find out, that is the biggest problem with this technology. Let's take a look at a mask. And by looking at the mask, we'll also see something about how mirrors are made. Here are 2 images, a SEM image and a tunneling electron microscope image of a photomask in cross-section. Here we see the multi-layer mirror. Very, very thin layers alternating, and a whole bunch of them that make the reflector. So in this region, light is about 70% reflective. Then we've got an absorber. Tantalum something, rubidium cap. I can't remember all the exact details of how this is made now, but you can see it's a multi-stack of materials that absorb the light rather than reflect it. Other than that, though, it really works in pretty much the same way as a transmitting mirror, And as always, the same optical Fourier optics principles apply. The diffraction pattern will be the Fourier transform of the mask pattern, etc. So in many ways, we think about imaging in exactly the same way with EUV lithography as with 193. Note, however, that the light is not normally incident on the mask. It, in fact, comes in at a degree of about angle of about 6 degrees, or maybe it's 7 degrees, something like that. And that has some interesting issues because of shadowing. Think of light coming at an angle, bouncing off. You're going to get some shadowing because of the height of the absorber. So that has to be taken into account as well. But the real issues involved with the mask have to do with defects. I think I've mentioned before that we have to be very careful about defects on the mask. Unlike a defect on the wafer, which can kill one die, a defect on the mask, if it prints on the wafer, will kill every single die that defect is associated with. So if you have, say, 4 die on one mask, one defect will cut your yield by 25%. That is completely unacceptable. As a result, we require defect-free masks. Any defect that might print on the wafer and be a killer defect when it prints has to be guaranteed to be eliminated. How do you do that? Well, at 193, we look on the mask with very sophisticated inspection tools. We find any defect that might print, and we repair it. We trim away absorbing material. We add absorbing material to any holes in the absorber. We fix every defect until we have a mask that is perfect. Or by perfect, of course, we mean good enough, so that there's no printing defects. Then we cover the mask with a pellicle, a very thin layer that is a millimeter or 2 away from, or 5 millimeters away from the surface of the mask. And this pellicle, transparent thin membrane, protects the mask from any defects, prevents any defects from landing on the surface of the mask. And so once we've guaranteed that the mask is defect-free, we then ensure that it stays defect-free with a pellicle. Well, at EUV, we can't really do any of these things yet. We have a lot of trouble making defect-free mask blanks, the multi-layer mirror surfaces that we're going to build our absorbers on top of. Then we don't have adequate inspection technology that can find every defect that might print. And once we find defects, we don't have adequate repair methods yet. In particular, if there's a defect in the multi-layer mirror, we have no way of fixing it. So usually if we find a defect there, we have no choice but to throw the mask away, unless that defect happens to be underneath an absorber. But most importantly, we don't have any pellicles. Without a pellicle, it's hard to guarantee the mask will stay defect-free during manufacturing. So, 2 approaches. We're going to try to develop a pellicle. Very, very difficult, but we're working on that. And we're going to try to keep our tools as clean as possible to make sure that no defects ever land on the mask. That's never been done before. We'll try it and see if we can make it work here. So this is a big challenge. The biggest challenge for EUV lithography is the source. We've had a lot of problems making a reliable source that produces high intensities of light. There's several different approaches, but the most the source type that's furthest along, the one that's getting the most attention, is called a laser-produced plasma, or LPP. The laser-produced plasma looks something like this. We have a source of liquid tin, and we drop tin through a hole, and it falls down. This little tin droplet then is zapped by a CO2 laser, extremely powerful laser with a wavelength of about 10 microns. And it just hits that tin droplet, it absorbs the energy, and it vaporizes the tin and turns it into a plasma. And it's the plasma of tin that releases the light. And it happens to release light at about 13.5 nanometers. This light then goes in all directions, but we collect as much as we can with this a mirror. So again, this is a multi-layer mirror that reflects 13.5 light and focuses it down to a point here called the intermediate focus. We then try to collect as much as possible of the debris, the zapped, evaporated tin. It just explodes everywhere. And one of the big problems is damage to the system because of all the tin debris. It's a fairly difficult source to manufacture, especially if we try to get high intensities. We have to have our droplets coming very quickly and very high-powered lasers zapping it, and well, it's just proven to be quite difficult. So, what are the problems with the laser-produced plasma sources? Well, it's not bright enough. We are between a factor of 10 and a factor of 100 too dim in the brightness of our lasers. As a result, our laser-produced plasmas, that is, as a result, our throughput is too low. We would like our tools to be able to operate at 100 wafers an hour, 150 wafers an hour, something in that range, to have good manufacturing. But instead, we might be operating at a couple of wafers per hour today. So anywhere from a factor of 20 to a factor of 100, too slow for what's required for manufacturing. Of course, we can work on improving the brightness of these sources, and if we can do that, then this might be practical. There's also reliability issues and uptime issues. So far, these sources have not been able to run 24/7 for days and weeks at a time. The source availability is only 70%, mostly because very frequently we have to go out and replace this collector because it gets all damaged from tin, which tin debris mitigation is the next problem. And again, the long-term reliability and the impact of all of these new technologies is still unclear. The third issue that we have to deal with to make EUV lithography a success is the photoresist. We're actually quite a bit far along in this project because it turns out that resists that are very similar to 248 and 193 resists, that is, chemically amplified resists, seem to work pretty well for EUV lithography. They just need to be modified rather than developing a whole new platform, a whole new technology of photoresists. So we're using resists that are quite similar to what we're used to, which is a big advantage. But that doesn't mean it's easy. One of the problems is without a good EUV light source, the resist manufacturers have had a hard time doing all the development experiments needed to create these materials, and as such, maybe we're a little bit further behind than we would have liked to have been in resist development. But the biggest problem is something called the RLS triangle. R is resolution, L is line edge roughness, or LER, and S is sensitivity. And we find that it's very, very difficult to achieve all the things we want at the same time. I want good resolution, I want low edge roughness when we print, and I want good sensitivity. That is, I want to be able to run at a low dose. This is very hard to do. We're going to have a lecture later about line edge roughness because it's a fundamental limiter when we try to push feature sizes below 20 nanometers. And it's very hard to get low roughness of our edges when using a low exposure dose. Why do we want to use a low exposure dose? Because we don't have a very bright source. Without a bright source, to get the throughput that we want through our system, we try to run at low doses. But when we run at low doses, it's hard to get good resolution. It's hard to get print features that aren't very rough along the edges. So this is the main difficulty with the photoresist today. So what have we learned about EUV lithography? As always, you should be able to quickly and easily answer these questions. If not, go back and review the material. What is the current resolution limit of single patterning with 193 lithography? As you know, the reason we're developing EUV lithography is because of this resolution limit. Why does EUV imaging use only mirrors in the projection system? What are the main challenges in EUV masks? What are the main challenges in developing an EUV light source? And finally, what are the main challenges in developing EUV photoresists. Well, as you might have noticed, we've kind of transitioned away from what's happening in manufacturing today, which is 193 lithography, and we're beginning to use in manufacturing double patterning. And now we've started talking about some future technologies. Will EUV make it? Will it be a mainstream technology in the next few years? It's still up in the air. I'm a bit of a skeptic, but there's a lot of very smart people working very hard to make this a reality. So we'll see in the next few years whether it happens. But there's also other imaging technologies and nano-printing technologies that are in use. They're in use both in the semiconductor industry and in other nanofabrication applications. So for the next few lectures, we're going to talk about other nanofabrication approaches, things that may or may not have application in the semiconductor industry, but are very interesting and important for nanofabrication in general. So let's look forward to thinking of some other ways of printing very small things besides optical lithography. Till then.